Standard first order system. So a standard first order system, I'll show what is the standard first order system here. It is 1 divided by ST plus 1. This is what is called as a standard first order system, right? R of S is your input and C of S is your output, right? So if at all you want to split any system which is given like this, if you want to convert any system which is given like this into a closed loop system, a closed loop unity feedback system, I will show you how to convert. So if you want to convert this into a closed loop system, you should have to find out this transfer function, right? You should have to find out the open loop transfer function. So I am converting this particular system into what? I am converting this particular system into a unity feedback system, a unity feedback closed loop system, right? So I have to find out this open loop transfer function of this system. See, in this case h of s is equal to 1, which means open loop transfer function is nothing but just g of s here, right? So if I find out g of s, I will get what to put here, right? Therefore there is one simple thing how to find out g of s. So this is your closed loop transfer function, right? Closed loop transfer function t of s, let us say, or else you can use m of s. M of s is equal to numerator polynomial of s upon denominator polynomial of s, that is equal to 1 by st plus 1, right? So from this, if you want to get g of s is equal to numerator polynomial of s upon denominator polynomial of s minus numerator polynomial of s, that is 1 divided by st plus 1 minus 1. So that is equal to 1 divided by st, right? So 1 divided by st is the transfer function here. I mean the open loop transfer function here. This is the open loop transfer function, right? So whether this system is given or else this system is given, we are talking about the same standard first order system. Is it clear? It is a standard first order system. Is it clear now? So you can find out the unity feedback representation of any particular system, right? Closed loop representation of any particular system, right? So for this particular system, let us say we are feeding a unit step input. Let us first feed a unit impulse input, a unit impulse input, right? Which means r of t is equal to what? R of t is equal to del of t. If r of t is equal to del of t, then what about r of s? R of s is equal to 1, right? If r of s is equal to 1, what is c of s? C of s is equal to 1 by st plus 1, simply, right? What is c of t? C of t is equal to Laplace transform of c of s. Sorry, not Laplace transform, Laplace inverse of c of s. So can you tell me what is the Laplace inverse of c of s? It is 1 by t e power minus t by capital T multiplied by u of t. 1 by t e power minus t by capital T. This is the impulse response of your standard first order system. So can you plot this impulse response? Just plot this impulse response, right? If at all I am plotting this impulse response, so this is an exponentially decaying profile, e power minus t divided by capital T, right? So as you are multiplying this with u of t, this is not present for 0 time, for time less than 0, right? For t less than 0, this is not at all present. So this is present only after t is equal to 0. So I am starting only after t is equal to 0. It will exponentially decay in this manner, right? So what is its value at t is equal to 0? Tell me everyone. What is its value at t is equal to 0? Yes, it is 1 divided by capital T. So this is the response of your system for unit impulse input, right? So let us calculate the response for unit step input, right? So if you integrate unit impulse, what do we get? If you integrate unit impulse, you will get unit step, right? So you will get u of t when you integrate unit step, that is equal to r of t, that is input is u of t, right? If r of t is u of t, then r of s is equal to what? R of s is equal to 1 divided by s. What about c of s then? C of s is equal to r of s multiplied by the transfer function t of s, that is equal to 1 by s into st plus 1, isn't it? Right? So just find out c of t. In order to find out c of t, you have to separate c of s into its partial fractions, right? So just separate this into its partial fractions. What are its partial fractions? You can partially factorize it as a by s plus b by st plus 1, right? A is 1 and a is 1, b is not minus 1 by t, b is minus t. A is 1 and b is minus t, which means we get minus t here. Yes, therefore c of t is equal to Laplace inverse of c of s, Laplace inverse of t by st plus 1. See, Laplace inverse of 1 by st plus 1, what did we get? 1 by t e power minus t by t u of t, right? Yes, very good. Laplace inverse of t by st plus 1, what you will get? Just multiply t with this, you will get e power minus t divided by capital T multiplied by u of t. E power minus t divided by capital T multiplied by u of t. Therefore, c of t is equal to 1 minus e power minus t by capital T multiplied by u of t. This is your answer. C of t, this is your output, right? So see here, we just have to plot this. We just have to plot c of t. So how to plot c of t? What is its value at t is equal to 0? Tell me. Its value at t is equal to 0. Value of c of t at t is equal to 0. How much is the final value? At t is equal to 0, response value is 0. As t approaches infinity, response value is 1, right? Which means the response is going to reach 1 like this. Exponentially, it will start at t is equal to 0 and slowly it will reach this 1 finally, right? So this is the response of your standard first order system for a step input. For a unit step input, this is the response, right? So just differentiate the unit step response once. Differentiate the unit step response and put t is equal to 0 in that. Differentiate the unit step response and put t is equal to 0 plus in that. Put t is equal to 0 plus. Tell me the value of d by dt of c of t at t is equal to 0 plus. Value of d by dt of c of t at t is equal to 0 plus. So just differentiate this. If you differentiate this, 1 minus e power minus t divided by t u of t, right? You could use uv rule, right? U dash v plus u dash v plus u v dash, right? So differentiate this, what you will get? You will get 0 minus 1 by t multiplied by minus e power minus t by t. So you could use the differentiation of this also, but I am telling you one simple thing. See, in control systems, as far as control systems is concerned, wherever you see 1 minus e power minus t into u of t, right? If at all you want the differentiated response of this, just differentiate this part. You need not differentiate this, right? So wherever you see, you can also differentiate this, but you should know how to arrive at the exact value, because even if you differentiate this, this will be present only at t is equal to 0, right? So see, Shivam Singh, I'm going to tell you why, right? So you just differentiated this, you got the differentiation of this, right? So this multiplied by u of t, u dash v plus u v dash 1 minus e power minus t by t into v dash. Differentiation of u of t is what? What is the differentiation of u of t? It is del of t. Del of t, right? Right. So if you differentiate u of t, you are getting del of t. So you have to put t is equal to 0 plus, right? So del of t is present only at t is equal to 0 and nowhere else, right? So just put t is equal to 0 plus. At t is equal to 0, the value of this is 0, right? 0 multiplied by anything is anyways 0. So only this will be present with respect to time and this will be 0 with respect to time, right? So if you put t is equal to 0 plus, this will become 0, right? And this is also 0, right? This will eventually lead to 0, and what is the need of unnecessarily computing the value of differentiation? Is it fine, right? So if you put t is equal to 0 plus in this, what are you getting? You will be getting minus 1 by t. It is minus 1 by t. Sorry, it is not minus 1 by t, it is plus 1 by t. If you put t is equal to 0 in this, minus of minus plus, and e power 0 is 0, it is plus 1 by t, right? So what is c of t? C of t is this curve. C of t is this particular curve, right? If you are differentiating c of t, what are you finding? If you are differentiating this c of t, right? So what are you finding for this curve? Aren't you finding slope? Yes or no? Yes, you are finding slope of this curve by differentiating it, right? So slope at what point? Slope at t is equal to 0. You are finding out slope at t is equal to 0. What is this? This is nothing but slope at t is equal to 0. Slope at t is equal to 0. I mean exactly 0 plus, right? So slope at t is equal to 0 plus means what slope? Which slope? Initial slope. Initial slope of the response. This is nothing but initial slope of the response. Initial slope of the response is how much? 1 by t, right? So if at all I want to draw a tangent to this particular curve at this particular point, I just want to draw a tangent to this particular curve at this point, right? So how is the tangent going to be? The tangent is having a slope of 1 by t. So this is the tangent, and this particular tangent is having a slope of 1 by t. So tell me, what is the equation of this tangent? Equation of this tangent is equal to y is equal to mx or not? Using y is equal to mx, tell me the equation of this tangent. Y is equal to 1 by t multiplied by t, right? Y is equal to 1 by t multiplied by small t, right? So final value of your response is 1. So I am saying you here one simple line. Just try to observe it clearly, right? If the response rises with the initial slope, right? If the response rises with initial slope, right, it would reach the final value in how many seconds? So just answer me. If the response rises with the initial slope, it will reach the final value in how many seconds? If the response rises with the initial slope, it will reach the final value in how many seconds? In order to reach 1, it requires t seconds. This small t should be is equal to how much? T. Only then the response becomes equals 1, right? So if the response rises with initial rate of rise, it takes how many seconds? T seconds to reach that particular final value, right? So t, what is t here? T is nothing but t is called as time constant of the system, right? What do we call t as? T is called as time constant of the system. Time constant of the system. So take down a definition for this. If the unit step response of the system rises with initial rate of rise, then it reaches the final value. It reaches the final value in a time period called, in a time called time constant of the system. Is it clear? Right? So what parameter is time constant? If at all the unit step response reaches the output with the initial rate of rise, you can see here the step response is not reaching with the same pace, right? So it has started with the pace, later on its pace has slowed down, right? Its pace has slowed down, right? Therefore, if the unit step response rises with the initial rate of rise, then it will reach the final value within how much time? Within t seconds, right? What is t? T is called as time constant of the system. Did everybody get it? Is it clear, everyone? So see here, let us, what is the response we have? It is C of t is equal to 1 minus e power minus t divided by t u of t, right? So let us calculate C of tau, C of capital T. Put capital T in the place of small t. In the place of time, put capital T. What you will get? It is 1 minus e power minus capital T divided by capital T, which means e power minus 1. 1 minus e power minus 1 into u of t, right? So what is the value of this? Please tell me here. Calculate the value of this. 0.6321. Very good, right? So C of 2t, C of 2t, it is 1 minus e power minus 2 capital T divided by capital T. It is e power minus 2 into u of t. What is its value? C of 3t also. C of 3t is equal to 1 minus e power minus 3. C of 4t, 1 minus e power minus 4. C of 5t is equal to 1 minus e power minus 5. 0.8646. What is this value? 0.9502. 0.9816. Next value 0.9932. Very good. So what is our final value? Final value is 1, right? So 0.6321, this value, I can call this value as 63.2%, 63.21% of final value. Can I call it like this or not? Tell me, can I call 0.6321 as 63.21% of final value? Yes or no? Yes, right? So similarly, I can call this 0.8646 as 86.46% of final value. 86.46% of final value. Yes or no? This value I can call it as 95.02% of final value. Right? So 95.02% of final value. This is 98.16% of final value. 98.16% of final value, and this is 99.32% of final value. So see here, so the time taken by the response to enter plus or minus 5% range of final value, right? See here, this is plus or minus 5% range of final value, let us say, right? This is plus or minus 5% range, right? The time taken by the response to enter plus or minus 5% range of final value. How much is it? How much is the time? It is 3 times of time constant, yes or no? Right? The time taken by the response to enter plus or minus 5% band of final value, right? You can call this band C. At exactly at this point, what is the value? It is 0.95. This is 1. This is 1.05. Right? The time taken by the response to enter this band is how much? It is 3 times of time constant. Right? Similarly, the time taken by the response to enter plus or minus 2% of final value band, how much is it? That is 4 times of time constant. Reply yes or no. 4 times of time constant, right? So 4 times of time constant is the time required for the response to reach 95%, that is plus or minus 5% band of final value, right? So plus or minus 5% band of final value. Similarly, 3 times of time constant is time to reach 98%. Time to reach 98% of final value, that is plus or minus 2% band, plus or minus 2% band of final value. I'm sorry. This is 3t and this is 4t. I've wrote it reverse. This is 3t and this is 4t. Very good. Thank you for reminding. I was just testing you, right? So, see here. It is the time taken by the system to reach plus or minus 5% of final value. How much is that? It is 3t, right? So the time taken by the system to reach plus or minus 2% band of final value. See, what we are assuming is, we are assuming that 5% of error is acceptable, right? 5% of error in the output is acceptable. So we are accepting even if 5% error is there, and we are assuming that our system has settled to its output even at 3 times of time constant, right? If 5% error is acceptable, we are considering 3 times of time constant as settling time. We are assuming that within 3 times of time constant our system has reached its final value, right? Our response has been reached its final value, right? So if 5% error is not acceptable, only 2% error is acceptable, then we are considering 4 times of time constant as our settling time, right? So we are calling it as TS, settling time for 5% tolerance band is equal to 3 times of time constant, and settling time for 2% tolerance band is equal to 4 times of time constant. Just note this, right? So TS, what is TS? TS is settling time. Settling time. What does settling time means? Settling time means time required to reach the output, right? This is called as settling time, and we are assuming our system has reached its 95% of output. Then 5% of error is only present. That is fine. We are assuming that to be fine, right? So just tell me whether this concept is clear or not. Settling time is 4 times of time constant or 3 times of time constant, depending on the acceptable percentage of error, right? So if 2% tolerance is acceptable, right? If 2% is the tolerance, then 4 times of time constant is the time settling time. Or else if 3% or else if 5% is the acceptable level of tolerance, then 3 times of time constant is the settling time. Let us say we have 2 systems with us, right? So let us say we have 2 different systems with us in our hands, right? So one system has a settling time of 10 seconds and another system has a settling time of 20 seconds, right? So system 1 and system 2, system 1 and system 2, right? One system has a settling time of 10 seconds and another system has a settling time of 20 seconds. So tell me which system among these two is faster? Yes, the system which has a settling time of 10 seconds is faster, right? So this is faster means 4t for this system, or else 4t or 3t, right? 4t or 3t for this system is less than 4t or 3t for this system. Yes or no? Tell me, if this system is having a settling time of 10 seconds, 4 times of time constant for this system is less as compared to 4 times of time constant for this system. Yes or no? Right? Which means time constant for this system 1, let us call it as T1, is less than T2, time constant of this system. Yes or no? Time constant of this system is less than time constant of this particular system, right? So this time constant term, time constant is directly available to you from the transfer function itself. What is the transfer function? It is 1 by st plus 1. So if it is not some standard system, it is having a DC gain other than 1, right? Here the DC gain is 1 for a standard first order system. DC gain is 1. If it is not a standard first order system, it is of some other system, then the DC gain is some other value, right? So the time constant is not going to vary, right? The time constant is directly available to you from the system's transfer function itself. Therefore, whichever system has less time constant, that system is said to be what? Faster. So time constant is giving you a measure of speed of the system, right? Yes or no? So if we have two systems, one settles faster and one settles slower, right? So we are comparing the speed of both the systems by saying that one system is fast and another system is slow, just by comparing their settling times. Settling times are depending on what? Time constant, right? So we can directly state a system which is having a lesser time constant is faster. So time constant gives a measure of speed of response of the system. Time constant gives a measure of speed of response of the system. So take this point, this is very important. Time constant gives what? It gives a measure of speed of response of the system, right? So if time constant is smaller, if time constant is a smaller value, if time constant is a smaller value, then that system is said to be faster. That system is said to be faster. So you have got an idea what time constant represents. Time constant directly indicates the speed of response of your particular system, whatever the definition of time constant might be, right? So time constant gives a measure of what? Time constant gives you a measure of speed of response of your particular system. Is it clear now? So see here, so we have studied the response of the system for two different inputs, right? Impulse input and step input. Let us study the response of the system for a ramp input provided. For a unit ramp input, when you provide a unit ramp input, so unit ramp input means what is R of t? R of t is equal to t times of u of t. Yes or no? What about R of s? R of s is equal to how much? 1 upon s square. Very good. Right. So if R of s is 1 by s square, what about C of s? C of s is equal to R of s multiplied by T of s, the transfer function. That is equal to 1 by s square multiplied by 1 by st plus 1. Therefore it becomes 1 upon st plus 1 multiplied by s square. This is C of s, right? So how can you write C of s? Split it into partial fractions using this partial fraction technique, that is a by s plus b by s square, or else take a by s square plus b by s plus c by st plus 1. Tell me the values of a, b and c. See, just multiply, take an LCM and multiply, that's it. So a into st plus 1 plus b into st plus 1 plus c into s square, right? So just compare both the numerators. This is the numerator, right? So if at all you take LCM s square into st plus 1, you will get this, right? So this is equal to 1 by st plus 1 into s square. So this denominators gets cancelled. Just compare the numerators, right? So take all the terms where you have s square, bts square plus cs square is equal to 0, because there is no term containing s square at all. Sorry, a is equal to 1. You can directly get a from that, right? So look for s terms, at into s plus b into s is equal to 0. So just solve these two equations, you will get the values of b and c, right? So just solve them. So there is no s square term, right? Just solve these two equations. Put a is equal to 1 in this. If you put a is equal to 1 in this, you will get b is equal to minus t. If b is minus t, then c is equal to what? Put b is equal to minus t in this particular equation, you will get c is equal to t square. Therefore, a is equal to 1, b is equal to, a is equal to 1, b is equal to minus t, c is equal to t square. These are the values. Everybody got the same values or not? So it is a by s square plus b by s plus c by st plus 1. Therefore, in the place of a you will put 1, in the place of b you will put minus t, in the place of c you will put plus t square, right? So find out c of t. What is c of t? C of t will be is equal to, right, if it is 1 by s square, you will get t, and it is t by s minus t plus Laplace inverse of this, you will get t e power minus t by capital T into u of t. So t minus capital T plus t e power minus t into, plus t e power minus t by t divided multiplied by u of t. So this is the response of your system, of your standard first order system, for what input? For a ramp input. So for the same, just plot this response. Just plot this response on a graph. Plot this response on a graph. So what is its initial value? Tell me the initial value of this response. What is the initial value of this response? 0. Yes. If you put t is equal to 0, this is 0, right? What about this? This is plus t and this is minus t. Initial value is 0. Right? Initial value is 0. So now look at this. See, as t approaches infinity, not only infinity, as t becomes large, as t increases, as time increases, as time becomes large, what happens to this term? This term will die out to 0 or not? As time increases, as time approaches a large value, what happens to this? This term will die out to 0, right? So if this term dies out to 0, what is left? The only thing left is t minus t, right? So can you compare this to the equation of a straight line? Y is equal to mx plus c. Y is equal to mx plus c. Can you compare this? Yes or no? What is its y-intercept? Y-intercept is minus t. Yes or no? Minus t is the y-intercept. Therefore, this particular straight line, if I draw this particular straight line, how is this straight line going to be? What is its slope? Slope of this is going to be 1, right? Therefore, the graph starts at 0. The graph starts at where? 0, right? So, what is the input? Input is ramp. Input is like this. Input is ramp, just like this, right? So, the graph starts at 0 and slowly, exponentially, it merges with this particular straight line, right? The graph starts at 0 and slowly it merges with, as time approaches infinity, as time becomes large, as time increases, what happens to this? This dies out, which means as time increases, the the graph of this will merge with this particular straight line in an exponential profile, with an exponential profile, right? The y-intercept of this is how much? That is minus t. Minus t is the y-intercept, right? Which means, see here, the distance from this point to this point, what is the distance? The distance is t units. Yes or no? The distance is t units, right? Likewise, at any instant, at any particular instant, as time is large, at any particular instant, the distance between these two lines, between the input and the output, is how much? How much is this distance? That the distance between those two lines, between the input and output line, as time approaches a large value, is how much? Capital T, right? Yes or no? Therefore, I can say under steady state conditions, the difference between input and output is how much? T. So take down a note. Under steady state, the difference between input and output is T units. See, this one, this blue one is this equation. So I will write the equation for each and everything. So equation for this is y is equal to t. Equation for this straight line is y is equal to t minus capital T. Whereas this red one has an equation c of t is equal to t minus capital T plus t e power minus t by capital T. So did you understand this note? Under steady state, the difference between input and output is how much? T units, right? So I can call it as what? I can call it as, that is, the steady state error of the system for ramp input is T units. So here, of course, we are just, right? So under steady state, the difference between input and output is T units, which means, see here we are dealing with transient response only, but still we can see about steady state error from the graph itself, right? So what do you mean by steady state error? Steady state error, you can define steady state error as, see here, steady state error represented by E suffix SS, right? Steady state error E suffix SS is defined as ESS is equal to limit t tends to infinity E of t, right? So what is E of t? E of t is nothing but the difference between input and output. Limit t tends to infinity R of t minus C of t, right? This is nothing but your steady state error. This is what is the definition for steady state error. Limit t tends to infinity R of t minus C of t. This is your steady state error. In the previous case, in the case of a step response, right? What was the steady state error? Can you just say from the graph? See, you can calculate it mathematically, but saying if you can just look into the graph and you can say, then it is fine, right? So what is the steady state error? In the previous step response, see, this is the steady state value going to be like this. And the steady state value of input is how much? That is also 1. 0, right? Very good. See here, the difference between the steady state value of input and output, steady state value of input is 1, as well as steady state value as time approaches infinity, the steady state value of output is also 1. The difference between them is how much? 0. There is no difference between them, right? If at all you want to calculate mathematically, you can calculate for step response as well as ramp response, right? So I'm calculating. Can I erase this? Can I erase this part? Right. So what is the step response? Let us calculate steady state error for step response as well as ramp response. So ESS for step input, right? So your input is U of t. R of t is what? R of t is u of t. What about C of t? C of t is 1 minus e power minus t by capital T multiplied by u of t. For a step response, this is what you got, right? Therefore, calculate ESS. ESS is equal to limit t approaches infinity R of t minus C of t. So u of t minus u of t e power minus t by capital T. So if you take this minus, if you take out this bracket, so you will get minus here, you will get plus here, right? So put t is equal to infinity in this. Put t is equal to infinity in this, you will get the answer. If you put t is equal to infinity, what happens to this? This becomes equal to 0, right? So as t approaches infinity u of t, what is the value of t approaches infinity u of t? How is u of t defined? U of t is defined as u of t is equal to 1 for all t greater than 0. U of t is 0 for all t less than 0, right? So whatever the value of t, u of t is going to be 1 only. Therefore, it is steady state error ESS is equal to how much? 1 minus 1, that is equal to 0. Steady state error is 0, right? So let us calculate the steady state error in the case of ramp from this mathematical expression, right? So in the case of ramp input, ESS for ramp input, R of t, that is input, is what is input? R of t is equal to what? R of t is equal to t into u of t. R of t is t into u of t. What about C of t? C of t, do you remember C of t? C of t is equal to how much? T minus capital T plus t e power minus t by capital T multiplied by u of t. This is it, yes or no? So just multiply this with u of t, you will get t u of t minus capital T into u of t plus t e power minus t by capital T multiplied by u of t. So this is your C of t, right? So R of t minus C of t, what will you get? Limit t approaches infinity, R of t minus C of t is, R of t is t u of t. This minus t u of t, I am just subtracting this from this, right? Plus t u of t minus t e power minus t by capital T u of t, right? So this and this gets cancelled here itself, right? If you put t is equal to infinity in this, what will you get? This will become 0. What about this? U of t as t approaches infinity is 1 only, right? So you are left with what? You are left with capital T. Capital T is the steady state error. So you can calculate graphically as well as mathematically. Is it clear, everyone? So let us look at various responses we got. So what is ramp? T times of u of t. This is nothing but ramp, right? So if we differentiate ramp, what do we get? Step. We'll get u of t, right? So if I'm differentiating this, I'm indicating with this blue mark, right? If we differentiate step, what do we get? If we differentiate step, we'll get impulse, that is del of t. If we integrate unit step, what do we get? If we integrate unit step, what do we get? If we integrate unit step, we'll get ramp, right? So if we integrate unit step, yes, if we integrate unit impulse, we'll get unit step, and if we integrate unit step, we'll get unit ramp, right? So this is the scenario. So what is the step response? what is the ramp response? You remember ramp response, right? All of you remember ramp response, right? It is t minus capital T plus t e power minus t by capital T. Yes or no? This is the ramp response, right? So just differentiate this and tell me what are you getting. Just differentiate this part and tell me what are you getting. Yes, if at all you differentiate this response, you will get 1 minus e power minus t by capital T. Differentiation of this 1, differentiation of this 0, differentiation of this minus 1 by t into t e power minus t by capital T. Therefore, if you differentiate this particular thing, you are going to get 1 minus e power minus t, right? If you just differentiate this, what are you going to get? If you differentiate this, if you differentiate 1 minus e power minus t by t, what are you going to get? Differentiate 1 minus e power minus t by t. You will get, very good, it is 1 by t e power minus t by capital T, right? Which means, see here, you just differentiated ramp response, you got step response. You just differentiated ramp response, you just got step response. You differentiated step response, you got ramp response. Sorry, impulse response, right? So you have differentiated this and you got this, which means if you integrate this, you will get this or not. If you just integrate this, if you integrate this, you will get this or not. Yes, right? So if you integrate step response, you will get ramp response or not. If you integrate step response, you will get ramp response. Yes or no? Yes, right? Therefore, see, one important thing what you can notice here is, if you just differentiate the ramp response, you will get step response. If you just differentiate step response, you will get ramp response, impulse response. The same way, if you integrate impulse response, you will get step response. If you integrate step response, you will get ramp response. If at all if at all you want parabolic response, you can easily integrate this and you can get parabolic response. But you must be knowing the initial conditions. So we'll practice several problems on this also. You will come to know how to solve this, right? So this result is valid only for LTI systems. Valid only for LTI systems. Just because we have taken a standard first order system which is an LTI system to deduce this, right? So this result is valid only for what? Only valid for LTI systems. Is it fine? Yes or no? This result is valid only for LTI systems, linear time invariant systems. So let us look at some questions based on this. So the unit step response of a system starting from rest is given by C of t is equal to 1 minus e power minus 2t. The transfer function of the system is, right? So going by your procedure, going by the general conventional procedure, see here, this is G of s and C of s is its output, and what is its input? R of s is its input. Therefore, G of s is equal to C of s upon R of s, right? So C of t is given to you. What is C of t? C of t is 1 minus e power minus 2t into ut, right? So what is R of s? For unit step response, right? So this is unit step response, which means R of s is equal to what? 1 by s. So you have to find out C of s in order to find out G of s. What is C of s? C of s is 1 by s minus 1 by s plus 2, right? So just take the LCM of this, you will get s into s plus 2, and what are you going to get here? 2 by s into s plus 2. This is C of s, right? So in order to find out G of s is equal to what? C of s divided by R of s, that is 2 by s into s plus 2 divided by 1 by s, right? So you will get g of s is equal to what? 2 by s plus 2. This is the transfer function. If you go by conventional procedure, this is the procedure. This is the entire procedure, right? If you go by conventional procedure, right? But if at all you know, impulse response is the transfer function of any particular system, right? So you can go by one more simple procedure, right? So you have been given step response. Just differentiate step response, you will get impulse response. Impulse response h of t is equal to d by dt of c of t. That is equal to how much? Differentiation of this is going to be 2 e power minus 2t. So Laplace transform of impulse response, Laplace transform of h of t, Laplace transform of h of t is nothing but your impulse response, that is 2 divided by s plus 2. Laplace transform of this is nothing but transfer function. So you have solved it in just one simple step, right? If at all you know this particular result, it is going to give you very fruitful results, that it is going to solve your problems in one simple step, right? So is it clear?